All right. So 3-2, you said? 42. Okay. I probably should turn this guy on. Oh yeah, I love it. I knew there was another problem. Yeah, you and I were talking about the nth derivative thing, right? There is another problem like that earlier. All right, one of you guys is working. Let's see. B. All right, guys, so 42. Whoa. All right.
What page is that?
This is page 188, so section 3.2. And it says, all right, this will really trip you up if you don't. All right. It gives you what g of x is, and then it says find, what does this mean? What does that mean? All right, so let me solidify this idea real quick. Let me see, let me use a little bit of paper here. I am zoomed way the shit in, okay. So if I have an f, what does this mean? First derivative. And then what does this mean?
Second.
Holy shit.
Third.
Holy shit. But can you quickly see that I don't want to go to the point where I'm doing a tally and stuff?
Yeah.
So after the third derivative, we do this. And that's understood to mean fourth derivative, so then we do that forever after. So the problem gives you this, and then it says find this. So the thing you can't do is to try to directly just jump to the nth derivative. How would I find the 18th derivative of a function when I just take the derivative and then take the derivative of that and then take the derivative of that? Yes? Okay, so what tells you in this problem that you're not supposed to do that, because you'd have to stop when you get to what? What the shit is in? I don't know. So what you're looking for is a formula based on the nth derivative. So you should find a formula that works for any first, second, third. If n is 1, it would give you the first derivative. N is 2, give you the second derivative. So how the hell are you supposed to do that? Do a few derivatives, see if you see a pattern, right? That is how most mathematical relationships are discovered. Do a few things, see if there's a pattern, extrapolate. So what am I talking about? So how do you do G prime? What do I have to use here? Yeah, buddy. Let's do G prime together. So if I do it, what's the song? That's right. Then minus, the bottom gets a turn. And then what do I put this over?
E to the x.
E to the x squared, which is this. Are you guys good with that?
Yeah.
E to the x squared, I multiply exponents, right? Okay, I like it. So then what does that become? What's x prime? 1. So I get e to the x, and of course, what's the derivative of e to the x? E to the x. So I get g prime. What can I do with this? Factor out a e to the x, and I get left with 1 minus x, right? Intriguing. Maybe if I do a second derivative, what do you think maybe will show up here? Maybe. What do you think? 0. No. First derivative, there's a 1 there. Second derivative, maybe there's going to be a 2 there. You have to do it. You guys do the second derivative. See if you see a pattern. If the second derivative has a 2 here, then what would the nth derivative have here? If the first derivative has a 1 there, and the second derivative has a 2 there, what do you think the nth derivative is going to have there? Frickin' n. Yes? That's how patterns work, yes?
Can we cancel out one of the e to the x's?
Totally. Yes. I like it. That even makes it better. So you do the first derivative, you do the second derivative, you do the third derivative. By that point, you should be able to see a pattern. If I see 1, 2, 3 happening somewhere, that's probably where n goes, because that's what n is doing. Yes? Okay, maybe? You've got to do a few, see if you see a pattern, because that's the fundamental thing about math, is we look for patterns, and then we capture that pattern, so then I can find the freaking 828th derivative without actually having to do each derivative. Okay, maybe. Kayla. Or was that really just your question about how my day was going? Okay. And again, like somebody just said, I could cancel one of these out, so then it becomes even better. So my guess would be there's probably going to be a 2 where that 1 is. There might be a little something extra going on, but you'll have to keep going and see what happens. Maybe. So trust me, if you just do a few more derivatives, you should be able to see the pattern. We'll see how that goes. There's a problem later. What was the other problem you were doing?
This is 3-1.
In 3-1?
Yeah, 3-1, 66.
Yeah, in 3-1 there was a problem a lot like this. Right here. Find the nth derivative, same idea. Do a few, see if you see a pattern. Okay. Anything else? Yes.
So we're not supposed to like know the quotient and product rules for 3-1 yet, right?
Definitely not for 3-1.
Okay.
Yeah. That's so if you've had calculus before, that sucks, because when we were in chapter 2, you weren't allowed to do any derivative stuff. But even when you're in class, while you're doing section 3-1 homework, you cannot do any quotient or product because we officially don't know it yet.
Yeah.
You can only use in a section what we know up to that section. You with me? Okay, maybe. Everybody else? Any other questions? Yes?
When's the quiz on this, and what is it on? When's the quiz on this, and what is it on?
The next quiz we're going to have is probably going to go up to like 3, 4 or something. So it might be, let's see, probably next Wednesday or Friday. Most likely, what about next Wednesday? I made that sound like it was a question, but let's do quiz.
This Wednesday or the Wednesday after? Today's Friday.
Yeah, so there's no more this Wednesday, right? Yeah, me tripping. We're not
No,
going
I
to
mean
go back
like
through
this
time.
upcoming Wednesday.
This upcoming
Yeah,
Wednesday.
yeah,
Shit, yeah. Quiz 3-1 through 3-4. You want it Friday instead?
Yes. Thank you.
Fine. Okay.
Thank you.
Yay.
Appreciate you.
No worries. I'll just make it even harder now. Okay. Because you'll have even more time to get ready for it. You got to be careful when you get what you want. All right. Anything else? Homework? Okay. So last time we took the littlest, babyest step into chain rule. We didn't really even discuss what chain rule is. We just sort of talked about there's a problem that happens when I try to do a derivative of... Can you guys remember the official name for a function like this? If I have a function that's made of other functions like this. Say again? Yes. Composite or composite. Either way you want to say it. Just don't say composite. That'll freak me out. It sounds like a mineral. Okay. So let me see. All right, I got a really stupid example of this, and I don't care. It's really not easy to figure out, like a nice physical world example. You guys remember, anybody ever watch those crime shows where they're like, enhance, you know, and you're like, an actual forensic scientist, they're like, holy shit, that's not how anything works. You guys with me? So you're basically just zooming and also somehow increasing the resolution through magic.
Yes.
Right, so most crime shows actually live in the Harry Potter universe. We're gonna find out. Now think about this. What if I had a security camera? I was even thinking about doing. So I'm not gonna set it all up. security camera looking at my computer. And I zoom into a picture 3 times on my computer. And the guy looking at the security camera at the same time zooms in twice. So to me, this picture looks 3 times as big. The rate of increase was 3 per whatever, how long it took, right? So it went up 3 times. To this guy, how much bigger will that picture look than it did before I zoomed in, before they zoomed in? No. 6, right? Yes? 6 times big. Huh?
Can you repeat that
Yes.
whole thing?
So I zoom in on a picture on my computer 3 times. So it is 3 times bigger on my computer. At the same time, the person looking at the security camera of my computer zooms in twice. How much bigger to them will my picture look at the end of all that zooming? It'll look 6 times as big.
Why not 5?
Because what does that do to everything it sees? What does this do to everything it sees when they zoom in twice? Doesn't it make everything look twice as big? And if something on my computer now looks 3 times as big as it did, it's going to look 6 times as big to them because they doubled the size of it. So if something was 1 inch tall, after I zoom in, it's now 3 inches tall. Yes?
No. That just doesn't make any sense.
Listen, you can't say no after what I just said. Listen, if it's 1 inch tall on my computer screen and I zoom in 3 times, isn't it 3 times? Isn't it 3 inches? Okay. If they at the same time zoom their picture up twice, won't it look 6 inches tall now to them? If they zoom in twice, doesn't everything double in size to them? If they zoom in twice, doesn't everything double in size? Okay, so if mine now went from 1 to 3 inches, didn't it for them go from 1 to 6? Because they doubled. All right, so maybe that's not the best. I'm just trying to give you a physical world example of why we have to multiply the 2 zooms. We have to multiply the 2 derivatives, the 2 changes.
Kind of makes sense.
All right, that's fine. I wasn't even sure if it would make any sense to anyone. So as long as it kind of makes sense, okay. So what we discovered, let me just show you real quick what we talked about last time, because I like this example. If I have this, okay. So let's do this directly and indirectly. So what do I mean by that? Can't I rewrite f of x to be this? Right? And then of course, what's f prime of x?
18.
Minus 12. I love it. Right now, you need to start loving polynomial differentiation. Polynomial differentiation, you're my buddy. It's so freaking easy. It's beautiful. You need to be there either now or really soon. Okay. So if I naively believe that this derivative works like this derivative does, right? What's the derivative of x squared? So that would just come down and it would go down by 1, right? So if I believed that this is going to work the exact same way, do I get what I know? We know this is the right answer. There's no question about it, correct? Do I get the right answer then? No, obviously not, right? Exactly what am I missing? A multiple of what would make this equal that? And of course, the derivative of the inside is 3. So let me bring back this example that we all seem to hate. This is me tripling. To be really honest, I didn't even make the numbers match up with what I was saying, and they did anyway. If I triple the size of something and somebody else doubles the size of that thing, those 2 changes have to multiply. I have to multiply. That's why it makes sense. How do I make this work? What is the correct way to do this problem? Let's see. If I want to do this problem without multiplying this out, I have to do this. That comes down. That goes to the first power. But then I have to give the inside its turn. This idea of everybody gets a turn kind of keeps going with this. So within this doubling, what did this do? Didn't it triple? Right? I'm sorry, let me be really clear on what's happening here. And this is a 1, by the way, right? So let me rewrite this. Okay, I don't want to do too much at once. So that comes down. The power becomes 1 times the derivative of the inside. So the inside gets a turn. So what did I do? I took the derivative of the outside. How does something squared work? The 2 comes down, and the thing is 2 to the first power now, right? That's how that works. But the inside gets its own turn. So times, like we just talked about with the zooming, the times make sense, times the derivative of the inside. So this will be 2 times 3x minus 2 times, what's this guy's derivative? 3. So it'll be 6 times 3x minus 2. Which, of course, is the correct answer, yes? Okay, so there's this idea of an inside function and an outside function for chain rule. And let me see if you guys, let's see. Let me show you something. Let's see if I can just continue to freak you guys out. Everybody got this? All right. Let's go back to this here. Let me see if Jeff can make this hard. Okay, that didn't come out right. What's the derivative of this?
2x.
Now here's the thing. We've been doing chain rule this entire time. We have. The 2 comes down, 2, the power goes to 1, times the derivative of the inside. But what's the derivative of x? So we've been doing chain rule. This is why I really, chain rule always happens. It doesn't really do anything unless the inside is more complicated than x. Is everybody with me? What's inside the square? X. Its derivative is 1. It's not going to do anything. But chain rule still works. It always works. This derivative is 1, so thankfully Jeff didn't make that more difficult. So this is why we teach it this way, but I always kind of don't really agree with that. But so chain rule is always there. It just doesn't affect the derivative unless the inside is more complicated than x. Okay, I like it. All right. So what if I had this? So now you understand why I don't want to do it the direct route, meaning multiply that out 12 times. Could you? Yes. Do you want to? If you do, you're an interesting person. I kind of want to know if anybody wants. Sounds like fun. Let me do it. So they would never give you this problem before we got to this section. This is horrendous if you had to do it the old way. But what's the new way? What's going to happen now? What's the outside function? Let me start with this. What's the inside function, obviously? Yeah, this polynomial. So the outside function is 12th power. How does anything to the 12th power work? The derivative. What happens? The 12 comes down, and then the thing is now to the what power?
The 11.
So that rule doesn't change, right? I know how to do anything to the 12th power. 12 comes down, goes to the 11th. But now, like always happens, but I have to do it specifically now because the inside's more than just x. It gets its turn. So I highly recommend that you remember how we did the quotient of product? I kept writing the rule this thing times this thing prime, blah, 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 and then you do the derivative. Because if you try to do too much at once, you're going to forget things. So I write the rule. The outside function derivative times the derivative of the inside, and then I do that on the next step. So what's that going to be now? What's this guy? 8x minus 2. Cool. And then I can multiply these together. Yay! Bah. Yes?
What happened to the plus 1?
Oh. All right. So you're cool with this derivative is 8x, right? You're cool with this derivative is negative 2, I guess?
Yes.
What is the slope of a constant function? What's the slope?
0.
0. There, it went to 0.
Okay.
Yep. So really, basically, the beautiful thing about polynomials is that it just becomes all the powers go down by 1. Right? So this guy doesn't even have anything. It goes down to 0. Right? A derivative of a constant is just 0 because it would be a flat line. Another way to look at this is, what's the slope of this line? Yeah, the slope of this line is negative 2. Right? That's kind of like the way I did it the very first time we did multi-term polynomial thing. Okay, maybe? Yes?
So then, this is more so just like out of curiosity. So then, for solving the second derivative, it would be the product rule and the component
Yes, I
derivative.
love it. Look at you. So if I actually had to do G double prime, what's the main thing happening here? I'm way far away from everything. Sorry. What's the, all right. If I had to do another derivative, do you see how I have to use product rule?
Yeah.
And within that, I'd have to do chain rule. Jeez. Let's do it. That sounds fun. All right, let's do it. Don't blame him. I was going to do this eventually, but I can do it right now. So watch what I'm going to do to make my work easier. And I really want this to make sense. The overriding thing here is that I have a product of two things. It doesn't matter what they are. Product rule says derivative of one times the other plus derivative of the second guy times the first. Okay, right? They each get a term. Yes?
This is kind of off topic, but how do you write like the dy dx?
Oh,
The second derivative?
yeah, so this would be, all right, I love it. Let me do this. So G prime is dg dx, right? Now watch this. G double prime would be d by dx dgx dx. So I'm doing a derivative of the first derivative. So it comes out to be, let me write it here. It comes out to be d squared over dx squared. And then you can go triple prime and all that kind of stuff. Okay, now, what's the rule for product rule? How do I do product rule? Yeah, so it'll be the derivative of this times this. Of course, I have no room for this. Plus this times the derivative of this. All right, let me stop for a minute. Right? That is kind of beautiful. That step is a nice breath, just a rest, because all you're doing is you're writing the rule. You're not actually doing any derivatives. So the rule says derivative of the first times the second, and then the first times the derivative of the second. They each get a term. So I don't have to do any work there. It's sort of like a little breather in the middle of the problem. Now I can focus my attention on what needs derivatives. So what's this guy's derivative here? 96, and that's just times all this business. plus. Now what's going to happen here? So that is its own little problem. What happens here?
Chain rule.
Chain rule, exactly. Don't have a function inside of a function. So what I desperately want you to understand is, do I currently give a shit about anything else I wrote? No, my problem right now is this. It's by itself. Whatever the answer is going to go here. But I don't care about this other shit right now. I know this is a function inside of another function. I've got to do that. How does that rule work? What's this do? The 11 comes down. And now this thing is to the what power? Shoot, I need a 1 in there. Become a 1. Times the derivative of the inside, right? This is going to be exciting. Yeah, I think I managed it. Right? So again, I really want you to understand. Don't give a shit about all this. Don't give a shit about any of this stuff. That's my problem right now. Because that's the thing that's being taken the derivative. So how does it work? The 11 comes down. That goes down to 10. That's how anything to a power works. But the inside gets a term. So times that guy's derivative. Because students screw this up because they try to keep everything in their head. That's insanity. That is insane, right? Nobody can do that. We need to do everything in parts. Okay, so then I get 96. And then what happens? What's this guy's derivative? Let's see. Let me write this down in a better way. I'm going to put the 11 there. Is that cool? You guys see that? I'm going to put the 11 there. Then I've got my 4x squared minus 2x plus 1 to the 10th. And then what's this guy's derivative? Yeah. What I'm trying to do for myself is allow myself to focus on parts of this. There's no reason you have to have the whole problem in your head at once. That is insane, like I said. That is what some students seem to think they're supposed to do, which doesn't make any sense. I can't do that shit. I can't keep this whole thing in my head. All right, maybe. And then now to simplify this. All right. This is a little more than I wanted to do now, but let's see if you guys are cool with this. What can I pull out of this? Can I pull a number out? All right, let me ask this question. How many terms are in this expression right now?
5? No, 4. 2.
There it is. There's 2. I see one plus sign that's really out by itself. So there's this term, and then there is this term. Yes? What are terms connected by? Multiplication. What are they separated by? Plus minus. So there are 2 terms up here, yes? And again, that's the thing that screws people over with factoring is they don't even know how many terms they've got. So they kind of mess things up. You got to know going in how many terms. So now I can factor this thing. Can I take a number out of both of these? No. 11 and 96 do not share anything, correct? If that was 99, I could take something out, but I can't. Can I take any of these out? Is that in both? This has 11 of them, correct? This one has 10. So how many can I take out? 10. So I've got, all right, this is going to get exciting. I'm going to take 10 of these out. And that's all I can see at the moment, so let's see what we got. So if I take 10 of those out, I've got a 96 left here. I had 11 of these, so now I've got one of them left in there. Okay, so I'm not done, obviously. But I took 10 of these out, so what's left in this term? 96, and I got one of these things left because I took 10 of them out. Plus, what's left in the next term? 11 times 8x minus 2. Pretty gross, right? And then, I don't know. So that's good for now, I think. That's more than I wanted to do at the moment. Isn't that yummy? Isn't that just, look at that. And you're like, that's not only creepy, it's also the wrong word, Jeff. Yes?
So is that level of like complexity going to be something that we do later, or is this something that?
This is coming very, very soon.
Okay.
Yes. Okay. Good question. I just said I didn't want to do this like right now, but this is very, very soon in our future.
Okay.
Yes.
What happens if you take the derivative of this?
So, what do you think would happen? In fact, if I had to do another derivative, I would not have factored it. Because then I could just attack this, blah, 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 right? This would be a chain rule, blah, blah, blah. And then I would attack this, which would be a product rule, 3 times over. Yeah, all right. So you can see how this is going to get immensely disgusting pretty quickly.
Yeah.
Maybe?
All I ask is that we do like a bunch of examples when it does get to this, because it's
Yes.
really helpful to see it over and over. And
Yes.
Over again.
Yes. So this is a little too early. So if you're right now like, I don't have a freaking clue, that's fine. All right, so I probably should have held off on that. I wanted to get us more used to just chain rule before we start throwing chain rule inside of other shit. But this was good for right now, just to show you what's coming. Okay. Let me do this. Let me go ahead. Oh, that's cool. You want to learn Chinese numerals? Let me give you this. Actually, before I do that, let me do this. All right. So there's a couple different ways. So if I have this, okay. So here's the idea. All right. This is a method I don't use a lot, but I think I'm going to show you. If I say u is g of x, so u is a function of x also. This will be f of u. So yes, that's the fu function. If I then need to take this guy's derivative, so I need to do dfu dx. Okay. So here's one formulation for the chain rule. This is equal to dfu du times du dx. Holy shit. Right, now real quick, before I explain each of these parts, do you see how this works back out to be that? Now technically, these don't formally operate like that always, but here they can be seen to work this way. So on that level, does everybody understand? And I really want you to understand this next thing. What did I say about chain rule? It's all about take the derivative of the outside function. Obviously, what is the outside function in these? F. So take the derivative of the outside function times the derivative of the inside function. That's exactly what this says. And it's slightly more formal in this notation. At the same time, that notation makes it seem harder, I think, sometimes.
Oh yeah.
Right? But can you see what it's saying?
Yeah, but I just like f of g of x plus g.
I'm with you. I'm
times
with
g
you.
prime, yeah.
I'm with you. So I'm going to show things 2 different ways, and you guys can pick whichever way you like better. What was the other way I wanted to show you? Jeff, hello. I forgot. Did I write it down somewhere? Yeah. This is the way that it's more understood. This is kind of what we did before. If I want this guy's derivative, this would be f prime times g prime, right? That's a little more in your face. Derivative of the outside times the derivative of the inside. These are actually the same kind of things. Okay, now, let me give you this. Oh, that's right. All right. We're gonna do one more thing before we look at this. You guys know. Oh shit! We haven't done this. That might be what happened. I might not have noticed my printer ran out of paper. I'm sorry. Let me see. Can you guys share? Thank you. And then of course, I go with that, but I'll figure it out. Okay. Now, something I don't know if this is in your brain at all. Do you remember what we do every time we kind of talk about a new thing? Don't we go back to the limit definition? Our favorite thing ever? Okay. So, if I want to do this, Jeff, you're not going to have enough room here. I'll get ready. Get out of here. Okay, if I want to do this, the limit definition is going to say this. I want you guys to all agree with me. Just bam, that's what the limit definition says, right? You put an x plus h in the thing, put an x in the thing, difference all divided by h. Yes? Good old y2 minus y1 over x2 minus x1. Now that looks like we can do nothing. Do you agree? It's like, what the hell are you going to do with that? Okay. Well, here's what you're going to do. You're going to do something equally as strange as when we added and subtracted the same thing. I'm going to multiply and divide by the same thing. So watch this. So where the hell did that come from? Well, this is going to feel a little bit like this, hopefully, maybe. It's basically that, just in more technical terms. No, Jeff, get out of there. All right, I really want you guys to see what I just did. So all I did was I divided by this, and I multiplied by this. So didn't I overall just do nothing? So it's the same thing. Do you guys agree? What's the limit as h goes to 0 of this? That should look very familiar. That's the definition of what? Yes, so g prime. Now here's the weird thing. What is this? What's the input? What's the inputs here? What's the inputs? X plus h and x. And below there is their difference, correct? What are the inputs here? G of x plus h? G of x. And what's it being divided by? The difference. So isn't this still y2 minus y1 over x2 minus x1? Isn't it still output differences divided by the input differences? So isn't this the limit? Isn't that limit f prime Jeff of g of x? We just recaptured. Now to be really honest, there's kind of some technical shit here. I'm not going to focus too much on that technical shit. But we just recaptured this. We are closer. This gets us closer to a true full proof. Okay, yes?
Can you show the process one more time?
So all I did was write what the limit definition needs. And I want you to realize some motivation for what we do next. What should be on the bottom of this is the difference of the inputs, yes? So if I divide by g of x plus h minus g of x, I better multiply by that same thing at the same time. It's just like the plus minus thing we did. Does that make sense? If I multiply the bottom, it's legal if I also multiply the top.
Yeah.
Okay, so that's all we did here. But it was motivated by, if only this was down here, that would look like a derivative. Well, now it's down there. And the cool thing is, the weird thing we had to do actually leads to its own derivative. That kicks so much ass. All right, now, Jeff being so nice to himself, I did not give my, can I borrow yours for a second? Okay. So what I've tried to do on here is show you the difference between what we can do without the chain rule and what we cannot do without the chain rule. Very obviously, hopefully, all of these have inside functions. Do you guys see what I mean? Yes? And then I kind of captured these kind of things again. And then I gave you an example here, and an example here, and let's do these together. Let me write those down. I'll give it back to you there. Because I don't know if you looked at the back of this yet, but there's a bunch of fun for you guys here in a minute. All right, so these should be pretty straightforward now. Let's see, the trig functions are relatively new to us. They're derivatives. If I were you, I would have the derivative stuff we know so far sitting next to you as you do homework. I mean, that would only make sense. But who remembers, so real quick, what's the outside function here? Sine. And the inside function, of course, is x squared. So what is the derivative of the outside function? Right? Is that cool? Derivative of sine is cosine times, and I think on this paper I kind of like the way it said this. It's called the chain rule because you're linking things. So I'm going to link to this the derivative of the inside. So what is the derivative of the inside? 2x. I'm going to throw that out front because it makes more sense as a coefficient. Okay. So what about this guy? This should be relatively easy now, right? We've done an example that was worse than this. What's the outside function? To the 10th power. Something to the 10th power. So I'm going to do that derivative, and then I'm going to give the inside a turn. Anything to the 10th power, how does it work? 10 comes down. And the thing is now to the 9th power. And then I give the inside a turn. Some of you guys are going to realize you don't always have to do this, right? I mean, some of you guys could just see that's 8x. But if I do this on the next turn, this guy's derivative totally is 8x. Is that cool? And I can just multiply that by 10. Is that also cool?
Yeah, I was going to ask. I was like, can you do that?
You have to. Yeah, you really want to collect all your coefficients. And then I got 4x squared minus 3 to the 9th. Chaboo! Let me do one more example that's not on there, because I think I gave you one like this. This has a function inside of a function. This has a function inside of a function. Could you have a function inside of a function inside of a function? Yes! And I always like to think about Russian nesting dolls, right? When does this end? Holy shit. All right. Russian nesting dolls. Do you know those? Yes? Okay. So what if I had, let's see, something not too crazy. Sure. Tangent of the square root of 3x squared minus 2. You see how this qualifies as a function inside of a function inside of a function, right? Do you even have to know that going in? No, you don't give a shit. There's an outside function which is tangent, and there is an inside function which is the square root of shit, right? That's all I have to worry about at first. You don't have to know ahead of time how many chain rules you have to use. There's no reason to know that ahead of time. So what is the derivative of, anybody remember? Yes, secant squared of stuff. Let me rewrite this. How can I rewrite this in a better form for what we have to do?
3x squared minus 2 to the power 1.
Kick ass. Times the derivative of that inside function. Let me stop for a minute. Right, so on the surface, this is not different than anything we've done yet. I do not have to know ahead of time. When I go to do this guy's derivative, then I say to myself, oh shit, there's an outside function and an inside function. So again, do I care about this right now? It's done. I don't give a shit about this. It's just going to come for the ride, yes? So don't let that again. I don't care. This is my problem now. And this is a relatively easy chain rule problem. It just becomes hard because it's inside this thing if you let that get in your head. So how do I do this guy's derivative? Let me write all this stuff down. It just comes for the ride. Whee! Times, how do I do the derivative of something to the 1/2 power? Say again, sorry.
Bring the 1/2 down.
Bring the 1/2 down. Now it's going to be to the,
-1/2.
and then the inside gets a turn. So, a huge mistake people make with chain rule is they keep going when they don't need to. There's people that will give more and more and more chains, more and more links. I'm going to be done after this. Do you guys see that?
Mm-hmm.
Is this another chain rule? No, it's just a freaking polynomial. No more links, right? Yes?
Couldn't you put the derivative of 3x squared minus 2 after you do the derivative of the inside to the half? Does that make sense? Like, could you put multiplication after?
Yeah,
Do
that,
you know what I'm talking about? Like, you could put that after the first step.
after the first step. Oh, yes, but
Okay.
people that do that are the ones that have extra links.
Okay.
You gotta trust me on this. So what she's saying is, can't you, on this step here, multiply by the derivative of that? Yes, but people that do that don't know where to stop. If you do it this way, you only do a chain rule when the thing you are taking the derivative of needs a chain rule. If you did it from the beginning, I always get people with more and more shit that you don't need. Oh, I don't know. So it's almost like you have to make this mistake before it makes sense. All right. So let's see. So that just came for the ride. What's this guy's derivative? 6x. And is everybody cool with this? That's going to be 6x times 1/2 is 3x. Yes? And then I could really, I don't know if you guys are cool with all this. This is 6x. 1/2 of 6x is 3x. I'm going to put that out front. I'm going to put that there. Is that cool? And again, you don't have to do all this in one step, but, and then I just write this stuff down. So that's been taken care of, that's been taken care of, and then I got this thing.
We don't need to set back from a fraction of root.
Well, that's neat.
We can leave it
Oh,
as
yeah, okay.
exponents.
Sorry?
We can leave those as exponents, like the 1/2 and -1/2.
Yeah, totally. Yeah, that's a more useful form. To be really honest, I wish we never came up with the square root and the roots notation. We don't need them. What's the 5th root? It's the thing to the 1/5 power. No? I don't know. You guys are all like, you don't like SOHCAHTOA. I don't give a shit what you think, man. But still, I wish we had never come up with that. It's stupid. This is the more useful notation. You almost always get the hell out of root notation immediately because it doesn't flow into any rules. All right, I'm sorry. Now, you guys, oh, did I give you back your thing? Yes.
Yeah.
Go ahead and turn that paper over and start doing what you can. Yes. Here. All right. What's this guy's derivative? Yeah. What's this derivative? 6x. What's 1/2 of 6x? So all I did was I pulled that out front because it's going to be a nice coefficient. I don't want to have it in the middle get lost in the middle. Yeah. And you don't have to do all that in one step. What's up? Yeah.